The first of two talks is going to be given by Alper Cakan on public key quantifier from classical oracles.
Hi everyone, I'm going to be talking about public key quantifier and keyfire from classical oracles. This is joint work with Vipul Gaila and Omri Shumeli. Okay, so one of the basic principles of quantum mechanics is the no-cloning principle, which says that given an unknown state, no adversary can create two copies of the state. And a related principle is the so-called no-teleportation principle, which says that given an unknown state, no physical process can convert this into a classical string from which the original state can be reconstructed. This is also called no-telegraphing principle by the work of Nehoran and Zhandry because in some sense we can teleport quantum states using entanglement. So to prevent confusion, I will also use this no-telegraphing name as the name of this principle. Okay, so these very simple principles of quantum mechanics are actually equivalent in the following sense. No-cloning implies the no-telegraphing principle because if you could telegraph a state, meaning that if you could convert it into a classical string, you can actually also clone it because you can just pretend to telegraph it and get your classical string. And since classical strings are freely copyable, you just run your reconstruction procedure twice and you get two copies of this original state. And similarly, no-telegraphing also implies no-cloning in the other direction because if you could clone a state, you can just keep cloning it until you have sufficiently many copies to do state tomography. And once you do the tomography, you get a density matrix, which is a classical string. So you can send it to the other party, and from that string, they can reconstruct the original state. A stronger version of the no-telegraphing principle is the so-called no-interactive telegraphing principle, which says that given an unknown state, even an interactive classical messaging process between two adversaries is not sufficient to transfer this original unknown state to the other party. So actually, even this no-interactive telegraphing principle is equivalent to the previous principles we talked about. Because if you could even interactively telegraph some unknown quantum state, you can do this, what I call the transcript duplication argument to also clone the original state. So if you could interactively telegraph the state, you can keep running the two independent instances of the second adversary until you get the exact same transcript twice. And since we get the same messages that is being sent from the second adversary to the first adversary, even though it has only a single copy of the original state, it can accurately answer the questions of the second adversary because it is only getting a single message. So it just needs to run its answering algorithm only once. And if we do this, we eventually obtain two copies of the internal final state of the second adversary, from which we know that we can reconstruct the original state. So we eventually get two copies of the original state. So as we've seen so far, all of these principles are kind of equivalent because no cloning implies no interactive telegraphing, which trivially implies no telegraphing, and no telegraphing implies no cloning. So in this general sense, they're kind of equivalent. But there's one major issue here, which is that all of these reductions or equivalences I've mentioned so far are actually kind of inefficient exponential time reductions. For example, going from no telegraphing to no cloning, we said that we need to perform tomography by first cloning the state sufficiently many times, but we know that to perform tomography in general, we need exponentially many copies of the original state. And similarly, going from no cloning to no interactive telegraphing, we did this transcript duplication argument. And again, given that the messages between the two parties can be of arbitrary length, in general, to duplicate this transcript, we need to keep running the second adversary, possibly exponentially many times. But in real life, we don't have exponential time. We can only perform efficient processes, which is usually modeled as polynomial time algorithms. So the question is, for the states that we can actually prepare in real life and for processes that we can actually perform in real life, are these simple principles of quantum mechanics really equivalent? So in previous work, Nehoran and Zhandry showed that relative to a quantum oracle, there's actually a collection of states that cannot be telegraphed efficiently using a single message, but it can be cloned efficiently. And more recently, Bostanci, Nehoran and Zhandry gave a candidate classical oracle separation of no cloning from no telegraphing. However, as shown by some recent work, as by Agarwal and Kundu, sometimes quantum unitary oracle separations might be misleading. So in this work, we generalize the previous results, and we show that relative to a quantum accessible classical oracle, there's a collection of states that cannot be telegraphed, even in the interactive setting, which generalizes even the unitary oracle separation, but it can be cloned efficiently. So this essentially means that no interactive telegraphing does not imply no cloning for efficient processes. Okay, so before talking about this separation, let me also talk about this kind of cryptographic formalization of the separation between cloning and telegraphing, as formalized by the recent work of Bostanci, Nehoran, and Zhandry. So we consider this primitive called quantifier. Where we have a bunch of algorithms. So we have a setup algorithm which outputs a public key and a secret key. And using the secret key, we have the spark algorithm that creates a so-called flame state, a quantum state, along with a serial number. And we have an efficient cloning algorithm which takes the public key and some flame state along with a serial number, and it perfectly clones this flame state into another register. And finally, we have a way of verifying an alleged flame state. And naturally, we require cloning correctness, which, as I said, clone algorithm must output a perfect or a near perfect copy of the original flame state when the flame state is honestly generated. And also, we require correctness of the verification, which means that given an honest generated flame state, we should be able to tell that it is really the honest generated flame state for that serial number. And for security, which essentially codifies what we mean by no interactive telegraphing, we consider the following security experiment. A challenger sets up the quantum fire instance by generating a public key and a secret key, and it also generates the initial flame state. And then efficient adversary is given this flame state, and it classically interacts with another efficient adversary, like they execute a LOCC protocol, for any polynomial number of rounds, and the messages that they're exchanging can be of any polynomial length. And at the end of this interaction, the second adversary tries to output a state that will pass the verification with respect to the original flame serial number. So essentially, the adversary receives this clonable state and is trying to interactively transfer this state to the other adversary through classical interaction. Right. Before moving on to our construction, let me talk about this primitive called one-shot signatures, which is one of the building blocks of our quantum fire construction. So one-shot signatures was introduced by Amos, Giorgio Chias, and Zhandry. And for one-shot signatures, we have this set of efficient algorithms where we have a setup which outputs a common reference string that will be available to everyone. And using this common reference string, anyone can generate a quantum signing key along with a verification key that can verify the signatures created by this signing key. And we have a signing algorithm that receives this signing key generated by the generation algorithm and the verification key and the CRS, and it can sign any message. Finally, using only the verification key, we can verify any alleged signature. And the main security requirement we want from such a primitive is the so-called one-shot security, which says that given this classical common reference string, no efficient adversary can create two valid signatures for two different messages with respect to the same verification key. So this also means that the signing key generated by the key generation algorithm cannot be cloned, because if you could clone it, you can sign two different messages. And the recent breakthrough work of Zhandry showed how to construct one-shot signatures in the classical oracle model. So let me give a high-level brief overview of our quantum fire construction, based on one-shot signatures. So essentially, the flame states of our construction will be purified versions of the one-shot signature signing keys that are generated by this janky algorithm. So in the original algorithm, you apply some unitary circuit, and at the end, you measure some part of the circuit to get your verification key, and the other part, the part that's not collapsed, is your quantum signing key. But in our construction, we purify this algorithm, and we don't measure anything. And cloning oracle will be essentially an encrypted version of the one-shot signature oracle that the original one-shot signature oracle lets you create signing keys. But in our modified version, this will be an encrypted oracle where to actually run this oracle, you need to have an initial one-shot signature key. And to verify an alleged flame state, we try to sign both the message 0 and then message 1, which kind of verifies that this alleged flame state is not collapsed to a classical string. But of course, as I said, we cannot actually sign two different messages, but we do this using a gentle measurement lemma where we sign, but we don't actually collapse to a single signature, and we verify in superposition. And let me also give a very brief high-level overview of the proof ideas. So for the purposes of this talk, I will talk about a simplified case where I'm assuming that the second adversary that's trying to reconstruct the original state on the other side is not allowed to access the one-shot signature key generation oracle, but it is allowed to access the verification oracle. So suppose for a contradiction that we can actually transfer this flame state from one party to the other party through classical interaction. Or again, for this talk, I will just talk about a single message from the first stage adversary to the second adversary. If we could actually do this, we can actually keep running the second adversary multiple times, and each time it will give us a flame state, which is a one-shot signature state. And by using the honest signing procedure of the one-shot signature scheme, we can actually obtain signatures for many different messages, possibly with different verification keys. But actually, we show that for the one-shot signature construction given by Nehoran and Zhandry, it's not possible to pack in too many different verification keys along with valid signatures inside a polynomial length message. So by this incompressibility argument, which applies even in the case where you're allowed to verify supposed signatures, we can show that if we just keep running this second stage adversary with this message from the first stage adversary, we will eventually get two different signatures with the same verification key. Because as I said, there's this incompressibility property that says that you cannot put in too many different verification keys. So eventually you're bound to get the same verification key twice. And getting the same verification key along with two different signatures for two different messages actually violates the one-shot signature security. So this will allow us to conclude the security of our quantum fire scheme, the untelegraphability security of our quantum fire scheme. But of course, in the general case, we're not considering only a single message from the first adversary to the second adversary, we're considering an interactive protocol. And of course, there's a high level of simplification here, where we assume that the second adversary is not allowed to access the signing oracle of the one-shot signature scheme. And we do more work to make the proof apply in this case too, because the simplified argument does not work in that case, because if the second adversary can also access the signing oracle, it doesn't have to obtain its signatures or flame states using this polynomial length message that it has received from the first adversary. It can actually possibly create new signatures, any number of new signatures along with different verification keys by accessing the signing oracle itself. So I suggest looking at our full paper for the complete case. And let me also briefly talk about the connections of quantifier to cryptography. So one of the big research areas in classical crypto is the so-called leakage resilience, where we assume that the adversary can obtain side information about the secrets that we are storing on our computer through side channels such as like measuring the power consumed by our computer that stores the secret key, or measuring even the electromagnetic radiation that's being emitted by the computer when it's operating on this classical secret key that we are storing on our computer. But in a recent work, we showed with my co-authors that if you can store your secret key in a special quantum encoding on your computer, you can actually tolerate any amount of side channel leakage on your secret key, which is classically impossible because if you're allowed to leak any amount of information from the device that's storing your secret key, you can actually just leak the secret key itself. But one issue with our previous construction was that this quantum encoding of the secret key that we have was a quantum state that is at the same time unclonable. And this is kind of problematic because when you're storing your secret key on your computer, maybe you will need to use that on a different computer in the future, or maybe there could be like decoherence over time and so on. So you need to you need to have a way of reobtaining this key in case you lose it somehow. But in this work, we actually show that it's possible, at least in an oracle model, to have a clonable quantum state that is still tolerant of any amount of classical leakage. So this means that, for example, if you want to use your key in a different server or computer later on, you can just clone your key and do that. Or over time, you can just keep refreshing your key by just cloning it so that it will be more resilient to decoherence and so on. And I think that's it. I can answer any questions.
Any questions?
Thank you very much for the talk. In the beginning, in your introductory slides, I stumbled upon one thing. So you formulated the kind of the problems of the idealized equivalence between all the theorems like the no-telegraphing, no-cloning, etc., as a time complexity problem, right? Like that it might be inefficient. But for the reduction from for the conclusion that you can telegraph if you can clone, there's even a problem if you can run in unbounded time, but your cloning is imperfect.
Yeah, that's a very good question. Yeah, I think in that case the equivalency does not apply. You're saying that like you can possibly clone maybe like with half fidelity or something,
or with like even with negligible error, right? Because you need exponentially many copies.
That's true. Yeah, I think that would be a good question for future work. But as you said, this equivalency, even in the information-theoretic case, it does not apply to imperfect cloning.
Right.
Yep.
Okay, I guess maybe I have a very basic question. So in the early slides, you mentioned that in the interactive case, you try out many different states and then you get a transcript and then you check for some matching transcripts. I didn't quite, I think I lost you a little bit over there.
This one, right?
Yes.
So I guess the argument is this. So suppose that some kind of interactive procedure between this adversary 1 and adversary 2 is possible, right? That means that when we run this protocol between the two adversaries, we know that the adversary 2 will accumulate some kind of internal quantum state over this interaction, right? And we know that using this local state that is accumulated, we can reconstruct this original state. But if I want to clone this unknown state, I kind of need to run this reconstruction twice. But we're running into this problem where this internal state of adversary 2 that we need to run a procedure on twice itself might be unclonable. So to get this, to get 2 copies of this final state, I just keep running independent copies of this adversary 2 until I get the same message, the same question to adversary 1. So that adversary 1 only needs to answer once because it's got only 1 copy of the initial state. Does that make sense?
That does actually, yeah. Thank you.
Thanks.
We have time for one more question. Okay, if there is none, then let's thank the speaker again.